morning. So, we have been discussing different supramolecular synthon. Let us see, I will just recapitulate for some 5-10 minutes. We discussed macrocycles, In macrocycles, we used crown ethers, and different other macrocycles. For example, Aja macrocycles, Thia macrocycles, Aja, Thia macrocycles, okay, all kinds of mixture. Then we took macrocycles with pendant arms, macrocycles with pendant arms. Pendant arms, 1 or 2 arms, and these are called, in case of ethers, ether, when the macrocycle is crown ether, then this pendant arm we call it lariat ethers, okay, lariat ethers. Lariat ethers, but generally we use this term pendant arms. Then we use macrobicycles, that is cryptands. So, I will write cryptands. From cryptands we discuss their synthesis and little bit. I do not claim that we have discussed at length, but at least some introduction. So, people who are interested, for them at the end of this entire lecture series, I will give them some key references for the synthesis of these kind of materials. Okay. So, after cryptands of different kinds we mentioned, and now we put, after cryptands we put, what did we do? Okay, we took, I keep forgetting things nowadays. All right, after cryptands we took spherands, Spherands is a particular type of cryptand, whether it is a spherical in shape. Okay. So, and then we put an important compound, just keep forgetting these things, calixarenes. We did a large number of, we spent some time in calixarenes, and we also did, after calixarenes, we did I do not remember all those things. Okay. So, we did several items, these are called supramolecular synthon. So, with these supramolecular synthons, we will now use them in different supramolecular situations. Okay. Our aim is to extract some useful properties out of these systems, so that we can make use of them. Because you have understood that unless we can make use of the compounds that we are making, those compounds will be called useless ones. So, but we are interested in making compounds and study them which are useful to us. So, from today onwards, I will start usefulness of these compounds in different situations. So, first I will say you that in the microscopic world, several events take place in the microscopic world, and we can conveniently see those events through something called fluorescence. So, fluorescence is an important technique. Fluorescence. Fluorescence, or sometimes they call also known as luminescence. So, this is an important technique through which we connect to the microscopic world. Whatever is happening in the microscopic world, we can, if that is purposely built through fluorescence, we can get there, we can know that event, particular event. And you know that fluorescence is a very, very sensitive tool. The reason being that I will explain to you. If you take, suppose you are measuring absorption spectrum, UV visible absorption spectrum. Okay. For absorption spectrum, for absorption studies, absorption is also very important. From the absorption spectra, I can recognize what kind of metal is there, what kind of geometry, so on and so forth. But these are not very, very accurate ones for our purpose. Okay. Why? Because absorption, usually we take solution maybe 10 to the power minus 2 molar, 10 to the power minus 2 to 10 to the power minus 3 molar. Not very dilute, but fluorescence is a very, very sensitive technique, and we take concentration say 10 to the power minus 6, 10 to the power sometimes 10 to the power minus 7 molar. So, it is a very sensitive technique, and the reason I will just explain to you. Okay. In absorption, I am drawing only the schematics. In absorption, phenomenon is a source of light, monochromatic light, is a source of monochromatic light. Okay. We do not worry about how to do this. So, this light goes through both, is a solvent, okay, solvent, and then sample, okay, is a sample. That means, we dissolve our compound in a suitable solvent and then put it in this cuvette, we call it cuvette, and then we put the same solvent where we dissolved our compound, same solvent in the another cuvette. This is called solvent front, solvent. And what do we measure? So, intensity comes through this is I0, and intensity come through this sample, suppose I. Okay. And what we actually measure? We measure in the equipment, we measure I0 minus I, okay, where I0 is quite some intense radiation, all right, monochromatic light, and I is also the sample has absorbed somewhat. Say I will write in a number, give a number, say solvent is 100, okay, and say sample will absorb 10. So, that means 90 will come out. So, what we are measuring? That 10, okay, 100 minus 90, that is 10, that is what we are measuring. Because of that, we cannot. So, absorption spectroscopy is not that sensitive, okay, because we are measuring the difference of two intense radiation as a function of wavelength and all that, those things are there. So, here measuring the difference I0 minus I. So, that will give us what has been absorbed by the sample. So, this is not very accurate. If we have to, if we take 10 to the power minus 6 molar, we will not see anything. Okay. So, it is not very sensitive. How about fluorescence? Fluorescence is extremely sensitive. Fluorescence, I am going in a minute the fluorescence diagram. Fluorescence, just take my word for it now, fluorescence, we take a sample in a solvent and then we excite it and then stop it, we excite it, okay, and that excited molecules will come, excited molecules will come back to the ground state giving radiation, and we are measuring the entire radiation. So, just very crude I am doing. This is a ground state, this is an excited state, electronically excited state. Suppose I am taking a fluorescence system, we excite it and then it comes back giving off fluorescence, and we are measuring the entire. So, we are measuring entire is not I0 minus I, but we are measuring I completely. So, that is a lot, and that is why fluorescence is a very, very sensitive technique, and we can measure fluorescence of 10 to the power minus 6 or 10 to the power minus 7 molar compound, or sometimes less, more or less. Okay. So, that is why often in biological systems situations will arise where we need very, very small concentration of this kind of some materials, then fluorescence is a very, very sensitive technique. Okay, followed. All right. So, before we talk about fluorescence, the most important thing about fluorescence that we have to write a fluorescence diagram, that is called Jablonski diagram. Jablonski diagram, let me write Jablonski diagram. This is a simple form of Jablonski diagram I am writing. Okay, very simple form. So, here is your this is a electronically ground state. This is electronically first excited state. These are vibrational levels. First electronically first excited state. So, I write S1. Electronically second excited state, I can write S2. So, when I am exciting the molecule with radiation, molecule will absorb energy and it will go to these states. It can go to say it can go to this state, all right, and it can go to this state also. This state also, followed. So, just give me some time to manage this. Okay. Fine. So, this is absorption and we give. So, with the same H nu it is absorption, and what happens, these are vibrational different states. So, eventually this one will come down to this state. Okay. From if it goes to S2, the molecule will come down to S1 state, excited, first excited state, and also eventually it will come to this lowest vibrational state. So, both this one as well as this one, absorption, they will come down to this state. This coming down is known as internal conversion. This coming down is known as internal conversion. Internal conversion. And this is absorption, I told you. This is absorption. Okay. So, it comes to the, so all these molecule upon excitation can go to populate S1 as well as S2, but eventually through internal conversion they all come to the S1 state, and at the lowest vibrational level, this particular process is called internal conversion. Okay. Now, there is another state which I am coming later. Okay. This is called T1 state, triplet state. All right. And okay, so forget about that for a moment. So, from this ground state, vibrational ground state, in the first excited electronic state, it will come down. It has to come down, the molecule will come down giving fluorescence. Okay, it will come down giving fluorescence. It can also go to this triplet state, okay, through, is called intersystem crossing, is called intersystem crossing. And what happens from this triplet ground vibrational state, it can come down to this ground state. It can come down to this ground state. Okay. This is called phosphorescence. So, this is called phosphorescence. So, this is, I have drawn a Jablonski diagram, approximate. This is very approximate. Jablonski diagram is really a complex one, but we do not need to bother about that. The simplest is fine. Okay. So, if you forget about everything, just we talk about that whenever a molecule is excited. Now, the question is, does it mean that all molecules are will give fluorescence? No. Usually, fluorescence lifetime is 10 to the power minus 8 or 10 to the power minus 9 second. Fluorescence lifetime normally. Fluorescence lifetime is normally 10 to the power minus 8 to 10 to the power minus 9 second. Okay. But any molecule, if we excite, they will be excited to say first excited state, that is called absorption spectroscopy. What happens to those molecules? Do they give fluorescence? No, because in those cases their lifetime is almost 10 to the power minus 12 seconds. So, before fluorescence they all come down, okay. There is no fluorescence, they give no fluorescence, they come down and via non-radiative pathway by giving off heat, okay, they come down to the ground state eventually in a generally molecule, but there are some molecules for which, so this is a property of molecule fluorescence. Some molecule or we call fluorophore, that is fluorescence active. So, those fluorophore molecules upon excitation go to the excited state and then spend their 10 to the power minus 8 to about 10 to the power minus 9 second. Some even go to picosecond also, all right. So, it depends upon the fluorophore, structure of the fluorophore and so on and so forth. So, that is why not all molecule gives fluorescence, but only certain molecule give fluorescence, we call them fluorophore. So, we call them fluorophore. Fluorophore, that gives fluorescence, and their excited state lifetime is 10 to the power minus 8 to 10 to the power minus seconds, or little bit slightly here and there also. And how about phosphorescence? Phosphorescence even delayed, much delayed, because we have from singlet to triplet state. So, spin multiplicity is changing, that is why that is a difficult process. So, it takes some time, phosphorescence. We do not worry about phosphorescence now, because before phosphorescence comes, fluorescence has already taken and we are happy with the data and all that, all right. Another important thing, when I have written these lines, I tried to put them vertical, okay, in my hand, so it does not look like vertical, but they are absolutely vertical, they should be in a vertical lines. Why vertical? Because this axis, it gives us idea about nuclear separation of the fluorophore, okay, nuclear separation. So, we assume that because nuclei are very big compared to electrons, because these are electrons are jumping. So, nuclei are very big, and so a mota man cannot move fast, he will be slow. So, similarly nuclei are slow moving, but electrons are very tiny particles, they move fast. I have told you already the time all that. So, therefore, we assume that the nuclei are stationary, they do not move. So, that is why they are vertical, okay. That is why I put vertical line, and that is called Franck-Condon principle, that I just said is known as Franck-Condon principle. Franck-Condon, I think I am telling the spelling all right. Okay, let me see. Franck-Condon principle, that is what I was thinking, does not look right. CK, Franck, now it is all right. Franck-Condon principle. Nuclei are assumed to be stationary when this thing is taking place. Fluorescence going up and coming down are taking place, all right. So, this is about, I do not think anything else I am missing, okay. So, you have to know this Jablonski diagram. I do not expect you to know in detail, but at least some salient features of Jablonski diagram and this time, about some time lifetime, fluorescence lifetime, and then the lifetime of absorption excited state in an absorption non-fluorophores, they come much faster, and fluorescence so will be slower that compared to that. All right. So, this is about the fluorescence. Now, with this fluorescence could be we could make use of this fluorescence phenomenon in purposely built systems, fluorophores, supramolecular systems. Purposely built systems. Okay, let me go to the next. Purposely built systems, that means what I am saying, let me first write the systems. We can put here this we call receptor. Receptor. My macrocycle, it could be a macrocycle, it could be a cryptand, okay, it could be a calixarine, so on and so. So, these are receptor. A receptor accepts an analyte. An analyte means it could be a metal ion or it could be any species, non-metallic species also. And here I have drawn a line that is called spacer, space. Spacer, and this one is fluorophore. This one is fluorophore. Fluorophore. So, this is receptor, this is spacer, and this is fluorophore. This is one configuration and very popular configuration. I will show you. So, this configuration. Okay. Another configuration is receptor and fluorophore are integrated, receptor and fluorophore. So, from now on my receptor would be, we signify like circle, and fluorophore will signify like a rectangle kind of. Okay. So, this is integrated, receptor fluorophore integrated. Receptor fluorophore integrated, and here receptor fluorophore is connected through a spacer. So, which means that which is easy to design. We want many different kinds of design. Okay. This one is very easy to design because I independently can vary my fluorophore and I can independently vary my receptor. And spacer is not only separates these two, they serve important purposes. As we go along, it will be obvious to you. All right. So, in a supramolecular systems that uses fluorescence, we have two main designs. One is receptor and fluorophore through spacer, and the other is receptor and fluorophore integrated. They are kind of difficult to synthesize. However, we will see one by one we can do. Okay. So, what I am saying, All right, maybe the time is not there. So, right now, so today I stop. Next time I will start mechanism of sensing. So, I will be starting in the next class something called mechanism of sensing. Okay. I will start mechanism of sensing. Thank you very much.